Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is section 1.4, which is a trig function review. So let's start. Now, first, let's consider a right triangle. All right, and here's my right triangle with base angle theta over here. I'm gonna call this side down here A, this side over here B, and this side over here I'm gonna call it C. Right? Now, in here there are 6 possible different ratios that we can come up with. All right, we can do things like B over C, or A over C, or B over A. We can also do the reciprocals of these, right? C over B, um, C over A, and A over B. Notice there that if I call A the adjacent side, if I call B the opposite side, and C the hypotenuse, and by the way, this is called the adjacent side because it is adjacent to the angle. It is right next to the angle, right? That's what adjacent means. Over here, this is the opposite side because it's opposite from the angle. It's the opposite side from the angle. So if I have B over C would be the opposite over adjacent. A over C would be the adjacent. Oh, hold on, not opposite over adjacent. Opposite over hypotenuse. All right, all right. Because C is the hypotenuse. Over here, we have adjacent over hypotenuse, and B over A, that's opposite over adjacent. Over here, C over B, that's a reciprocal of these, so it would be hypotenuse over opposite. It would be hypotenuse over adjacent, and adjacent over opposite. Now, if if I think about this data down here, all right, if I think about this data that I just recolored in blue, what we can say here is we can rename all these as sine theta, cosine theta, tangent theta, cosecant theta, secant theta, and cotangent theta. Notice that all the ones on the right hand column over here, these are all the reciprocals of the left hand column. So the reciprocal of sine is cosecant, the reciprocal of cosine is secant, the reciprocal of tangent is cotangent. All right. So in here, these are the 6 trigonometric functions. One thing to notice, let's look at tangent. All right. If I look at tangent, and well, that's b over a, right? So one thing we're always allowed to do, all right, no matter what we're doing in math, there's there's a few things we're always allowed to do. One of them is add 0. The other thing is multiply by 1. So I'm going to multiply by 1 here. 1 over c over 1 over c, right? Now what is that going to do? That's going to give me b over c over a over c. Now why do I care about that? Well, let's look at what b over c was. B over c was sine, and a over c was cosine. So what we found here is that tangent can also be rewritten as sine theta over cosine theta. All right. So tangent is just sine over cosine. By similar logic, we would say that cotangent theta is equal to uh, cosine theta over sine theta. All right. So that's the 6 trigonometric functions. All right. The best way to remember this, all right, the best way to remember this is using the acronym SOHCAHTOA. SOHCAHTOA. And that allows you to remember these first three, right? Because it's sine. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. All right, so that helps you remember this entire column right here. And then after that, it's just remembering that the reciprocals would be, well, they are what they are. All right, so now let's uh, let's recall something else. Let's talk about the Pythagorean theorem for a second. The Pythagorean theorem also is always brought up when we talk about right triangles. So let's think about the Pythagorean theorem. It says, given a right triangle, right, with sides A and sides B and hypotenuse C, then we have that A squared plus B squared is equal to C squared. Now let's look at this equation. A squared plus B squared is equal to C squared. Right? Again, that's only true with right triangles. So in here, what we're gonna do is, well, one thing that we're always allowed to do with equations is, if you do one thing to one side, you must do it to the other side. So I'm gonna multiply both sides by 1 over c squared. All right, that's the same thing as saying dividing both sides by c squared. Now, what happens when we do that? Well, what I end up with here is a squared over c squared plus b squared over c squared is equal to 1, which can then be rewritten as the quantity of a over c squared plus the quantity of b over c squared is equal to 1. Now let's look at these right here, a over c and b over c. A over c was cosine and b over c was sine. So what we can do now is we can rewrite this, all right? We can rewrite this now as cosine squared theta plus sine squared theta is equal to 1, because a over c was cosine and it's being squared. B over c was sine and then it's being squared. Now in general, we don't really remember it in that order. We like to remember it as sine squared theta plus cosine squared theta is equal to 1. All right. Now, let's manipulate that even more. All right. So in here, we're gonna be doing two different things. The first one over here, well, let's make those arrows bigger. The first one over here, we're going to be dividing by cosine squared theta. The second one over here, we're going to divide by sine squared theta. Now let's see what that gives us. If I take sine squared and divide it by cosine squared, well, that's sine over cosine, well, sine squared over cosine squared, sine squared theta over cosine squared theta, plus, then I have cosine squared over cosine squared is equal to 1 over cosine squared, right? So that was dividing by cosine squared, the entire equation. If I take sine over here, sine squared over cosine squared, that's going to give me tangent squared. Cosine over cosine, well, cosine squared over cosine squared is 1, and 1 over cosine squared, well, the reciprocal of cosine is secant. So then we have tan squared plus 1 is equal to secant squared. Now over here, if I divide everything by sine squared, well, what do I end up with? I end up with sine squared theta over sine squared theta plus cosine squared theta over sine squared theta is equal to 1 over sine squared theta. And what are these? Well, sine squared over sine squared, that's just 1. Cosine squared over sine squared, that's cotangent squared. And then 1 over sine squared, the reciprocal of sine, would be cosecant. So we have cosecant squared, right? And there, those three equations, which I'll surround in green. So these three equations are called the Pythagorean identities. All right. Now, Really, the only one, so let me write that down, Pythagorean identities. The only one that you really need to remember, though, is the first one, sine squared plus cosine squared equals 1. Because you can always come up with the other ones in the same fashion that I just did, by either dividing by cosine squared or by sine squared. All right. It is helpful to memorize them, though. All right. So those are the Pythagorean identities. Now we have some other kinds of identities. All right. So let's talk about the sum and difference formulas. Sum and difference formulas. And we'll only consider sine and cosine. So if I have sine of u plus v, that's going to give me sine of u times cosine of v plus cosine of u times sine of v. Notice that I kept the u's and the v's in the same order, uv, uv, uv. So a nice way to remember this is, well, it's sine, cosine, cosine, sine. Sine, cosine, cosine, sine. Right? Now that's when we have the addition of these two angles. If I had the subtraction, well, then over here, I would also have a subtraction. All right? And, excuse me. And that is the sum and difference formulas for sine. Now let's look at cosine. If I have cosine of u plus v, that gives me cosine of u times cosine of v minus sine of u times sine of v. So with cosine, it's cosine, cosine, sine, sine. All right. And again, notice that I kept the same order of the u's and v's. All right. Now let's say that I had a minus inside there. So if I had cosine of u minus v, well, that actually turns out to be cosine, cosine plus sine, sine. All right. So with the sine, the plus or minus stays plus or minus. But with cosine, the plus or minus becomes minus or plus. All right. So those are the sum and difference formulas. I won't go into too many examples of that. Actually, I won't go into any examples. Now let's talk about some the even and odd functions for this. Even and odd. Well, turns out there's only two even functions for the trig functions. They are cosine theta and its reciprocal secant theta. The rest are odd functions. So sine theta is odd, tangent, cosecant, and cotangent. Those are all odd functions. All right. Um, so really, the only thing that you need to remember is that cosine is even and it's reciprocal, and then the rest of them are just odd. There are uh, there's another identity that we should have discussed. So let's discuss it now. Double angle formulas. And again, I'll just discuss sine and cosine. So if I have sine of 2 theta, that's 2 sine theta cosine theta. All right. So that's how we can reduce that angle. If I have cosine of 2 theta, well, there's multiple ways to rewrite this. Right? We can say that's 2 times cosine squared theta minus 1. We can say that's 1 minus 2 sine squared theta. Or we can say this is cosine squared theta minus sine squared theta. All right, all three of these are all identities for cosine of 2 theta. So those are those angles. Now, let's real quickly discuss something called the unit circle. If you have never seen the unit circle, Well, actually, I'd be very surprised if you have never seen it. But let's if you have not yet memorized it, all right? If you have not yet memorized the unit circle, right now is the time to really take notes. All right. So the unit circle. Let's see, can I get a circle out of this? Yeah, that's a pretty good circle. Now, all right. So let's well, it's not really a circle. I think it's a weird polygon there, but it's close enough. Now in here, we're gonna split this up into the four quadrants, right? Now, the what you want to keep in mind here is that we're working here with angles, all right? And all the angles that we're working with are going to be in radians, all right? So in here, let's put this up a little bit more. So all the angles are going to be in radians, all right? And one more. So the easy angles first. Well, this is angle 0, this is pi over 2, this is angle pi, and this is angle 3 pi over 2, and over here it's 2 pi, which is equivalent to saying 0, right? Um, these angles, right? To remember them, well, you actually do need to remember these first three angles. And those first three angles are pi over 6, pi over 4, pi over 3, all right? So first, let's discuss how to remember all the angles. All right. In quadrants 2, in quadrant 2, all the angles are going to be very similarly drawn. So in here, pi over 6, well, over here, the one that's corresponding to the same height would be something pi over 6. The one that corresponds to the pi over 4 will be something pi over 4. The one with pi over 3 will be something pi over 3. All right. Now, what that something is very easy to remember. In quadrant 2, all the numerators are 1 less than the denominator. So this is 2, this is 3, and this is 5. All the numerators are 1 less than the denominator. So that's quadrant 2. Let's look at quadrant 3. Well, similarly, we're going to pair them up with the corresponding angles. So this right here is going to be something pi over 6, something pi over 4, and something pi over 3. Now in this quadrant, all the numerators are 1 bigger. All the numerators are 1 bigger than the denominator. So maybe I should have written over here, all the numerators are the denominator minus 1. Over here, all the numerators are the denominator plus 1. Now let's look at the second and the last quadrant here, quadrant 4. Just like before, we're gonna say that the angles are corresponding to them. So this is something pi over 6, this is something pi over 4, and this is something pi over 3. And it doesn't matter whether you looked at it vertically or horizontally, we're still end up with the same thing there. Now, in this quadrant, all the numerators are twice the denominator minus 1. Twice the denominator minus 1. So twice 6 is 12 minus 1 is 11. Twice 4 is 8 minus 1 is 7. Twice 3 is 6 minus 1 is 5. All right. And there we go. Now we completed all of the angles in the unit circle. So now let's look at all the coordinates at all these angles. So really, the first quadrant is really the only one that you need to memorize. All right. We'll talk about the patterns for the other quadrants. But first, let's talk about what happens at the 4 intercepts here. So over here at angle 0 or 2 pi, we have the coordinate, well, 1, 0. It's a unit circle after all. Unit circle meaning that the radius is 1. It's 1 unit. So if that's 1 unit, then yeah, the coordinate will be 1, 0. Similarly, this over here will be 0, 1. This over here will be negative 1, 0. And this last one down here, by 3 pi over 2 would be 0, negative 1, right? So those are all those angles. Those are the coordinates at all those angles. So now let's look at the first quadrant. Well, let's look at this real quick. Every single coordinate here is going to be over 2. They're all going to be fractions over 2. So that's the first thing that we want to do. They're all fractions over 2. The next thing you really need to do here is count to 3, right? 1, 2, 3, count to 3. So what we're going to do with that counting to 3, we're going to go down the x-axis, 1, 2, 3. And what I remember was down the x-coordinates, not the x-axis, down the x-coordinates. Counted 1, 2, 3. And then count backwards, going down the y-coordinates. So 3, 2, 1. The next thing is everything gets a square root. All the numerators get square roots. So square root of 3, square root of 1. Well, the square root of 1 is just 1, so we don't really write it. The square root of 2, the square root of 2, square root of 3, and again the square root of 1, we don't really write. And there you go. That's the first quadrant, all the coordinates there. The last thing you need to recall here really is that in quadrant 2, everything is in the form of negative, positive. In quadrant 3, everything is in the form of negative, negative. And in quadrant 4, everything's in the form of positive, negative. So we can just finish building the rest of the circle now. At pi over 3, well, to look at 2 pi over 3, we're going to first look at pi over 3, and we're going to just rewrite that coordinate, but with a negative x value. So negative 1/2 comma radical 3 over 2. Similarly for pi over 4, write the same exact thing, but with a negative x value. So on and so forth. So negative radical 3 over 2 comma 1/2. And then over here in the third quadrant, so everything's negative, negative. So we're going to say this is negative radical 3 comma 2 comma negative 1/2. Negative radical 2 over 2 comma negative radical 2 over 2. And negative 1/2 comma negative radical 3 over 2. All right, and notice that all the parts where the angles are corresponding, like right here, the over 3, the pi over 3, the x value is 1/2, the y value is radical 3 over 2. The absolute values here, x value 1/2, radical 3 over 2. And that's a 2. Continuing this pattern here. Oh, so what I was saying with that is that it happens also with the pi over 4s as well as the pi over 6, right? The x value radical 3 over 2, then 1/2. All right, and every single one of these. So over here with the pi over 3, the x value is going to be something 1/2. All right, so the positive value is an x, okay. The y value is negative. Well, let's look at the y value. Negative radical 3 over 2. Cool. Then radical 2 over 2, comma, negative radical 2 over 2. And finally here, radical 3 over 6, comma, negative 1/2. All right, so those are all the coordinates of this unit circle. And again, it's a matter of remembering how to build it, really. It's not so much memorize the entire thing. One last thing I want to talk about here is, as far as this trig stuff goes, I want to show you, or remind you at least, what the trig functions look like, right? So if I have something like y is equal to, so, well, actually, graphs of trig functions. Now I mentioned them in other videos, in a previous video, but if I have y is equal to cosine x, right? Cosine looks like this. And it repeats forever. If I have y equals sine of x, then I end up with something very similar to the cosine. um, but it starts at 0 instead of at 1. Right? And lastly, let's look at tangent of x. Tangent of x also repeats, right? But it looks very different. It is not a wave. In fact, it's got horizontal asymptotes all over the place, all right? And they happen wherever cosine is equal to 0, in fact. That's good enough. So tangent looks like this. All right, that is the tangent function. And it repeats forever and ever, both ways. All right. So those are the basic trig functions that we'll be working with as far as the graphs, I mean. And that's the end of 1.4. This is 1.5, which is called inverse functions. All right, so here we go. So first let's recall how a function works. A function takes some element x, right, from the domain to some element f of x via some function f, right? Well, if we want to go backwards, so here we're going from some element x to its image. If we want to go from the image back to the original element, we'll have to do it using f inverse, all right? The inverse function. So that's the general idea of what an inverse function is. Now let's actually define it. So definition. In here, a function g is the inverse of the function f when f composed with g of x equals x for x in the domain of g, and g of f is equal to x, g of f of x is equal to x for x in the domain of f. All right. Now that's just my notation. That's not real notation for domain. All right. But I'm using it here. Now, in general, we denote, so G is denoted F inverse. All right. So in general, when these two things are true, F composed with G of x is just x, and G composed with F of x is just x. We would just denote it as F inverse. So what we would do there is we would rewrite these as F inverse, not F inverse, F composed with F inverse of x is just x, and F inverse composed with F of just x is just x. There we go. So that's how we will rewrite those. All right. Now, I want to make a note here. All right, and it's a big note. It's a big note here. All right, it's a very important note. F inverse is not 1 over f of x. All right, the inverse is not the reciprocal. All right, we're very, very used to saying things like a to the negative 1 is just 1 over a. And that's true as long as a is a real number. All right, but not if it's a function. right? If it's a function, the reciprocal is not its inverse, all right? If I wanted to rewrite the reciprocal with the notation of to the negative 1, I can rewrite it as f of x and then everything in brackets or parentheses to the negative 1. All right, that still would not be f inverse of x. All right, so again, in general, the inverse is not the reciprocal. All right, so let's let's do an example here to verify that two functions are inverses of each other. So verify that f of x being equal to 2x cubed minus 3 and g of x being equal to the cube root of x plus 1 over 2 are inverses. Alright, so let's do that. Well, what must be true? What must be true for them to be inverses? F composed with G must be X, and G composed with F must be X. Alright, so let's do that. So if I take F composed with G of X, well, what does that mean? That means F of G of X. And if you recall, that just means plugging G into F. So that would be 2 times um, G of X cubed minus 1. And G of X, well, we have a definition for that. So we have 2 times the cube root of x plus 1 over 2, everything cubed, and then minus 1, right? And from there, well, the cube root cubed, those cancel each other out. So what I end up with there is 2 times x plus 1 over 2 minus 1. And at that point, we say, well, the 2 and the 2's cancel each other out. So I have x plus 1 minus 1, which is just x. Good. Now let's look at g of f of x. Well, that's really saying g of f of x, right? G composed with f is just g of f of x. Now, what does that really mean? Here, that would be the cube root of f of x plus 1 over 2, right? I'm plugging in f of x into g. And what does that mean? Well, that would be the cube root of, well, what's f of x? 2x cubed minus 1. And all of this over 2. And, hold on, I forgot to do the plus 1 here. Plus 1. And then from there, we say, well, that this parenthesis here is not doing anything, so we have a negative 1 plus 1 goes away. So what I really have there is just the cube root of 2x cubed over 2. These two cancel each other out, so I have the cube root of x cubed, which is just x. Nice, good. So we just verified that they are inverses of each other. All right, so what we can say here is thus g of x is f inverse. All right, now that was verifying the two functions are inverses of each other. Now let's look at them on the graph in general. All right, so properties of inverse functions. So, well, let me actually just rephrase that. Reflective property of inverse functions. All right, so this is what it is. It says f and f inverse are reflections of each other about the line y equals x. All right, So let's see what that means. Let's make it a little more straight. There we go. The line y equals x is just a line going through the origin at a 45-degree angle, essentially. All right. So that's the line y equals x. Let's say that I had some function that looked like this. All right. This is my function f. Oh, all right. So that is in blue, we've got f of x. The inverse of that I will do in red. The inverse of that would look like this. So let's see. So that will be about there. All right. So something like that. All right. That would be the inverse function. They are mirror images about the line y equals x. All right. So in here, what we would say here is that any point here, any point AB in the function f exists in a function, and over here as BA in the function f inverse. All right. So in red, we had f inverse. All right. That'll be something similar to that. Now, in order to actually be a function, an inverse function, you need to make sure that it passes something. So this drawing, I will later point out what it fails. All right. So one-to-one functions. All right. So let's consider one-to-one functions. A one-to-one function, well, so a function is one-to-one if A equals B implies f of A equals f of B, and f of A equals f of B implies A equals B, right? So it must imply both for a function to be true. Essentially, what this means is no x and y repeat, all right? An easy way to remember what is a one-to-one function, well, it's something called the horizontal line test. All right? And the horizontal line test is as follows. A function f has an inverse if and only if every horizontal line intersects the graph of f at most one time. So it's very similar to the vertical line test, all right? But in here we're trying to use horizontal lines, all right? So that's going to be for the horizontal line test to figure out if a function is one-to-one. And if a function is one-to-one, then the inverse exists. So some examples of one-to-one functions. Well, this would be a one-to-one function, all right? Because no matter what horizontal line I draw, it always just hits it at most once. So this is one-to-one, all right? Now, let's look at something that would not be one-to-one. All right. If I had a parabola, well, a parabola is not one-to-one because I can draw a horizontal line to hit it twice. So this is not one-to-one. Well, one-to-one. There we go. Now it's possible to have graphs that might trick you into believing that they are one-to-one, that they are one-to-one functions. So for example, this right here looks like it might pass a horizontal line test. And in fact, there's no horizontal line that I can draw that would make this, uh, that would cross more than once. However, this is not a function. So this is not a function in the first place. Because it's not a function in the first place, in other words, it fails a vertical line test, who cares whether it passes the horizontal line test, because then it would not, it's not even a function. So since it's not even a function, you can't even talk about it being or having an inverse. All right. So this is not one-to-one. All right. And that's essentially what fails up here in my original drawing. The fact that I can draw a horizontal line there is what makes that fail. So technically, the drawing that I made there does not actually have an inverse. So that blue line F or that blue curve F is technically not a one-to-one function, so it would not have an inverse. But the idea still stands of it is a mirror image along the line y equals x. All right. So now that is to figure out um, if a function has an inverse. So let's talk about finding the inverse function when it does have an inverse. Finding an inverse function. Right now, again, it does need to be one-to-one. So a lot of times um, we want to make sure that they actually are one-to-one. And that's very hard to do unless you have a general idea of what function you're working with. Now in here I have 2x minus 3, the square root of 2x minus 3. All right. Now, what I want to say here is, well, the domain is wherever x is greater than or equal to 3 halves, and the range is from 0 to infinity. All right. Now this is just a square root function. We already know what a square root function looks like, right? So this, I mean, the 2 and the minus 3 are just transformations happening to it, but the overall idea still stands on what it looks like. Now, how do we find an inverse function? Well, we're going to start by rewriting as y equals 2x minus 3. Then we're going to rewrite it as x is equal to the square root of 2y minus 3. Notice that what I did there was I swapped the places of x and y. All right, now what I'm going to do is I'm going to solve for x. So, excuse me, solve for y. So I'm going to square both sides. X squared is equal to 2y minus 3. Solve for y. Y is equal to x squared plus 3 over 2. All right, but now one thing that we want to keep in mind with inverse functions. If I have the domain of a function f and its range, well, then the domain and range of the inverse will become the same but opposites. What do I mean? I mean now, well, over here, the f inverse of x, which is x squared plus 3 over 2, has a domain of 0 to infinity, but a range now of 3 halves to infinity. All right. So notice that the range of the inverse function is the domain of the original function, and the domain of the inverse function is the range of the original function. All right. Now those are just some of those functions. Let's quickly look at the inverse functions of trig. All right, so inverse trig functions. And in here, we're going to look at just two of them. All right, well, three of them, excuse me. We're going to look at y equals sine inverse of x, right? But actually, before I do that, let's first recall just what y equals sine of x looks like. All right, now in here, y equals sine of x, we know it looks like this. Right? Now, technically, this fails a horizontal line test. So because it fails the horizontal line test, it technically doesn't have a true inverse. But we know that we can just restrict this to just this piece right here. All right, that goes from 0 to, excuse me, that still wouldn't fail. That still wouldn't pass the horizontal line test. I meant to do from here to here, which is from negative pi over 2 to positive pi over 2. All right. Now, if we restrict it to just that region, then it does pass the horizontal line test, and then it does have an inverse. So what we're going to do is we're going to restrict it to that. And when we do that, well, we get the following graph. Y equals sine inverse of x. It would look like this. We have a maximum value at pi over 2, a minimum value at negative pi over 2, and this is going to be negative 1. Sorry, that's not what I meant to do. There we go. Negative 1 and 1. And this is what it looks like. Right? That right there is the graph of sine inverse. All right. If I look at, so notice that the sine inverse is bound between negative pi over 2 to positive pi over 2. All right, as its range, which makes sense because over here I cut the domain to be from negative pi over 2 to positive pi over 2. Similarly, the domain over here is restricted from negative 1 to 1, and that would be because the range over here for sine is from negative 1 to positive 1. All right. The other ones that I'll do would be cosine, cosine of x, which again has a very similar problem in that it is a wave and fails a horizontal line test. But what we can do there is we can restrict that one from here to here, all right? And that's from 0 to pi. And what we end up with over here as our function for cosine inverse, and let me just change the color there. So for that function, we end up with the following graph. Also from negative 1 to 1 as its domain, just like sine inverse. But now, let me actually shift this down. There we go. But now, it has a range from 0 to pi. Let's say that's pi. And this is what this graph looks like. It crosses at pi over 2, and it looks like this. It goes from here to up here, like so. There we go. So I'll leave it as that. All right, so that would be the graph of cosine inverse. All right, now let's look at the graph of tan inverse. So if I first look at the graph of tan of x, Whoa. Y equals tan of x. Well, we just saw, we know that it looks like this. And again, it fails the horizontal line test. So technically it doesn't have a true inverse, but we're going to restrict this to just the first region here. All right, so that's going to be from negative pi over 2 to positive pi over 2. And for the inverse of that, let's look at what that graph looks like. So this is going to be y equals tan inverse of x. And this looks as follows. It has two horizontal asymptotes, one at pi over 2, the other one at negative pi over 2. Notice that they were originally vertical asymptotes, and it looks like this. All right, so that is what tan inverse looks like. And notice that its range is from negative pi over 2 to positive pi over 2. All right, that is the end of 1.5. This is 1.6, which is exponential and logarithmic functions. All right, so in here, we're gonna first let's recall some properties of exponents. All right, and they are as follows. A to the 0 is equal to 1. A to the x times a to the y is a to the x plus y. If I have a to the x and then that to the y, this is just a to the xy. If I have ab to the x, this is a to the x times b to the x. If I have a to the x over a to the y, that's a to the x minus y. And that was supposed to look like an exponent. There we go. If I have, so those are just a bunch of properties. If I have a over b to the x, this is a to the x over b to the x. And lastly, if I have a to the negative x, I have 1 over a to the x. These are just properties of exponents, right? Now, in here, it's important to keep in mind how these properties of exponents work, because these properties will still be applying towards functions overall, all right? But let's look at how exponential functions look like. So graphs of exponential functions. Now, if I have, so let f of x be equal to a to the x, where a is greater than 1. Excuse me, where a is greater than 0, and a is not equal to 1. All right. In general, the domain is all real numbers. The range is from 0 to infinity. The y-intercept is the point 0, 1, and there is, so the y-intercept is the point 0, 1, there is no x-intercept, and in here the function f of x is 1 to 1. By the way, there's no x-intercept. That's assuming that you haven't shifted the function down, right? This is just for a to the x. Now, what does this look like on the graph? On the graph, well, we have two scenarios really, all right? And the scenarios are if a is greater than 0, we have that the function looks like this. If a is between, well, I said that wrong. Not if a is greater than 0. If a is greater than 1, there we go. If a is between 0 and 1, then it looks like that, right? So that's in general what that looks like. Now, let's think about what a being between 0 and 1 means. If a is between 0 and 1, well, it could be a fraction. It would be a fraction, right? So consider a being equal to some fraction, for example, 1/2. Then a to the x would be 1/2 to the x. But 1/2 is just really 2 to the negative 1. So it would be 2 to the negative x. Alright, now I point this out because if you think about it, this is just a reflection over the x-axis, over the y-axis, right? So that's what that negative 2 in that x would be talking about. So in here, if I have f of x there, I could write it as 2 to the negative x. And again, that would be just a reflection over the y-axis. Now, we also have a very special number here whenever we talk about exponential numbers. And that number is Euler's number. Euler's number. And Euler's number is a number E, which is approximately 2.718, 2.718, with a whole bunch of other values there, right? That is Euler's number. And Euler's number is no exception to being a real number, right? It's not a rational. In fact, it's an irrational number. So E is irrational, which means it cannot be written as a ratio, right? It cannot be written as a fraction. So we can essentially talk about f of x being e to the x. And e to the x will look like that, right? Notice that e is 2.7. 2.7 is bigger than 1, so we're in this first scenario there. All right. Now, that is exponential functions overall. Now, let's look at logarithmic functions. Right? Now, logarithms are just the inverse functions of exponentials. All right. So let me first define it first. So if I have log base a of x equals b, that's equivalent to saying that a to the b is equal to x. All right. Similarly, if I have, well, I'll just leave that as that. All right. So some properties of logarithms. So properties of logarithmic functions. Properties of logarithmic functions. So if I say let f of x be equal to log base a of x, where a is greater than 0 and a is not equal to 1, we have the domain is from 0 to infinity. The range is all real numbers, so from negative infinity to infinity. The intercept, well, we have an x-intercept being 1, 0, and well, along with that, there is no y-intercept, and it is a one-to-one function. All right. Now, in here, we have two scenarios again where a is greater than 0, a is greater than 1, or a is between 0 and 1. In general, we don't really talk about the second scenario here, but I'll just discuss it briefly. So if a is bigger than 1, that's what the function looks like, crossing at 1, 0. If a is between 0 and 1, technically it looks like this. Well, but that doesn't really come up that often, where our base is a fraction between 0 and 1. Right? Now, we can have log base b. Log base e. And log base e is just ln of x. Similarly, we can have log base 10, and log base 10 is just log of x. All right, this is just notation. And we use this notation to mean the common log and the natural log. All right, natural log and the common log. This is called the natural log because it's base e. E is also commonly known as the natural number e. All right, mostly because it comes up in nature a lot. So let's talk about some properties of logarithms. Right? So properties of logarithms. We have a product rule where if I have log base a of x, y, it's just log base a of x plus log base a of y. If I have log base a of x over y, that would be log base a of x minus log base a of y. And if I have the log base a of x to the y, that would be y log base a of x. All right. So let's see why something like this would be. All right. Now I'm not gonna prove these identities here, but let's just get a general idea. All right. Here I have a multiplication. A multiplication becomes an addition. Why would that be? Well, the idea is that if I have a multiplication on the base, it becomes an addition in the exponent. Similarly, over here, a division becomes a subtraction. So if I have a division, that becomes a subtraction. And over here, we have a log to a power. So if I have something to a power, it becomes a product of the powers. So these are essentially where these properties come out of, all right? A product becomes addition, a quotient becomes subtraction, and a power becomes a product, all right? So that's the general idea there. Now, we can use properties of logs to expand or condense statements. So let's say expand the following. So if I have ln of x squared plus 3 cubed, well, let's do that square just to keep track of the numbers. All of this over x times the cube root of x to the third minus 1. Using rules of logs, and now you don't need to be able to do this all in one step like I'm about to do, but you should be able to do some of this. And I meant to do x squared minus 1 there, not x cubed. All right. So in here, what we can say is this becomes 2 ln of x squared plus 3 minus ln of x minus 1/3 ln of x squared minus 1, which we can go ahead and rewrite as 2 ln of x squared plus 3 minus ln of x minus 1/3 ln of x plus 1 minus 1/3 ln of x minus 1. All right, so in there, notice that I rewrote this x squared minus 1 as x plus 1 times x minus 1. All right, so that was some mental arithmetic, but that's how we ended up with that. All right, and all I did there was I turned all the exponents into coefficients, right? The square became 2, this cube root became 1/3, and anything that I was dividing became a minus. And we can apply the same exact trick to condense, right? Uh, so if I have something like 3/2 times ln of x squared plus 1 minus ln of x plus 1 uh, minus ln of x minus 1, well, that would give me something like this. And I'll do this in 2 steps. 3/2 times ln of x squared plus 1 over x plus 1 times x minus 1, which would then be equal to ln of x squared plus 1 over x squared minus 1, and then all of this to the 3/2. All right. Now, that's just some basic examples of expanding and collapsing or condensing some logarithmic expressions. Real quickly, let's solve for x. Let's recall how to work with some equations here. So if I have 7 is equal to e to the x plus 1. Well, to solve for x there, I would start by taking the natural log of both sides and then subtract from both sides. Subtract 1 from both sides. So x is equal to ln of 7 minus 1. Similarly, I can start with something like ln of 2x minus 3 is equal to 5. And I exponentiate to get rid of the ln. So 2x minus 3 is equal to e to the 5. So therefore x is equal to e to the 5 plus 3 over 2. All right, and then whatever that value is. All right. Now these are 2 very simple examples of solving for x, right, with exponential and logarithmic expressions. I expect that you already had a lot of practice with this in Precalc. All right, that is the end of section 1.6.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.